You must have been surprised why we end up getting the whole of our environment getting powered from a single substance that gets mined from the ground. You've had a chance of coming across motor vehicles powered by diesel and petrol. You must have had a chance of getting jets getting powered by kerosene or paraffin. You have had a chance of getting kerosene lamps getting powered by kerosene. You must have had a chance of getting bitumen or asphalt getting used to tarmac our roads. The problem is, or the question is, where can we be able to get all these components that serve as fuel or raw materials for different purposes in our environment? We are going to answer this question using this question that I got in one of the chemistry papers that were done by the PEARSON EDEXCEL students in our country and in other countries all over the world. So looking at this diagram or this question, this is what you call fractionating column. So the whole of this part is called fractionating column. It serves a purpose of ensuring that the components of crude oil are well separated. So the process itself at large is called fractional distillation. For those who have had a chance of getting introduced to the methods of separating mixtures, you must have been told that fractional distillation is a method that is used to separate components, making a mixture in such a way that those components must first be one, miscible, two, have different but close boiling points. Very good. So the components making the mixture that need to get separated by fractional distillation as a method of separation must first be miscible. Two, have different but close boiling points. A good example can be this. When you want to actually separate water and ethanol, then we are going to use what we call fractional distillation. Why? Water and ethanol can form a mixture and they can get separated by fractional distillation. Why? Because one, water and ethanol are first miscible. So they actually get put together in a container, for example, and they do not form two layers, they form one layer. So using a separating funnel or decantation or a dropper cannot separate these two components forming this mixture. Why? Because they form one layer when they are put together to mean they are miscible. Number two, water and ethanol have different but close boiling points. For example, water boils at exactly 100 degrees Celsius when pure. Remember we said impurities raise the boiling point of a substance while impurities can still lower the melting point of a substance. For example, when water has an impurity or water has impurities, it will not boil at exactly 100 degrees Celsius. It will boil at a temperature higher than 100 degrees Celsius because of the impurities, ending up absorbing some of the heat transferred to the water during the heating process. When I put an impurity to water, when I put an impurity to ice, it may not melt at 0 degrees Celsius. Why? Because impurities are going to lower that melting point of this ice. And of course, melting means turning from solid to liquid. And of course, boiling means turning from liquid to gas. So the water may not turn to gas at 100 degrees Celsius if an impurity is found in it. And as well, the ice is a form in which water exists, in as far as solids are concerned, may not be able to turn from its solid state to its liquid state at 0 degrees Celsius. It may actually melt at a temperature lower than that if an impurity is added. And this is the approach scientists use in temperate countries to actually clear ice from roads. What do? They can add, for example, calcium chloride as a salt, which is now going to act as an impurity. So that this impurity is going to lower the melting point of ice from 0 degrees Celsius, for example, to negative 4 degrees Celsius. So this ice can actually melt faster and get cleared from the rods. You see, so that they can actually be able to have the rods being able to get used very well. So the ethanol can actually boil at 78.2 degrees Celsius when pure. 78.2 degrees Celsius when pure. So let's get back to this. So the process of separating components of crude oil is called fractional distillation. Why? One, all components of crude oil we are going to actually analyze here and be able to capture all here are first miscible. And apart from being miscible, they have different but close boiling points. They are miscible and they have different but close boiling points. So they are first miscible. Then number two, they have different but close boiling points. So we will actually be able to note this. Crude oil is impure and it has several components. To mean crude oil is a mixture. Crude oil is first mined from the ground. And of course, we have actually been told that crude oil can get formed when plants and animals are all buried in the ground or somewhere within the ocean. There's what we call decomposition. And when a particular layer of the earth has to actually get to that point of exerting some pressure on these animal and plant wastes, some geographical processes occur. And because of the heating that occurs within the earth's crust, you see, oil is actually able to easily get formed. So it gets mined. And once it has been mined, then it gets introduced in a heater. And within the heater, there's what you call heating. And the highest temperature that can get recorded is 350 degrees Celsius. And of course, that means you can't use a normal thermometer that you normally use in our hospitals to be able to actually record any change in temperature as far as this process is concerned. Why? Because this thermometer is going to crack because of this higher temperature that gets recorded during this process. So crude oil has been mined. It being a mixture and being impure, it actually gets introduced into a heater where heating gets done. And as temperature begins to get recorded, those components, those fractions of this crude oil that have a lower boiling point will be able to turn into vapor. You see? And they get collected as different fractions. For example, you need to know that you have what you call liquefied petroleum gas or refinery gas. This becomes the first component or fraction of this crude oil that gets collected at 25 degrees Celsius. I repeat, LPG or RG, refinery gas, becomes the first fractional component to get collected when it first turns into vapor when the temperature reaches 25 degrees Celsius. So it distills off and gets collected as the first fraction. The second one is petrol, and petrol can get collected after the temperature reaches 70 degrees Celsius. So petrol at 70 degrees Celsius gets collected as the second fraction. We have naphtha, and naphtha can actually distill off at 120 degrees Celsius. So these are just estimates of the temperatures you're supposed to actually record when this process gets carried out in the industries. And of course, the fourth fraction to actually get considered is what you refer to as kerosene, and you can also be able to call it paraffin. And this can actually get collected or can actually distill off at 160 degrees Celsius. So at 160 degrees Celsius, we are expected to collect kerosene or paraffin. And you can also have diesel, and diesel can get collected at around 260 degrees Celsius. That is diesel is our other fraction to get captured here. We have what you call lubricating oil at around 300 degrees Celsius. Very good. So these temperatures can just be able to get given as rough estimates. They can either be lower or more than this. So we always pick this as our working values in terms of explaining this concept. And we have fuel oil at around 340 degrees Celsius. Okay, and we can have the last one getting called bitumen or residue, or you can also call it asphalt, and this can distill off at 350 degrees Celsius. So those are the main components that can form crude oil. In its impure form, in its useless like form, when it gets mined from the ground, it can actually end up getting heated up to a maximum temperature of 350 degrees Celsius, so that at the end of the day, quite a good number of fractions can get collected, 8 in number. RG, petrol, naphtha, kerosene, diesel, lubricating oil, fuel oil, and bitumen, residue or asphalt as our last fraction. So 8 fractions or 8 components ending up when put together to form crude oil. Look at that. And the major part of it is this: they are all miscible to form one substance called crude oil, and they have different but close boiling points, making it easier for them to distill off at different temperatures and get collected differently or separately. So, okay, you need to know this. As you move downward from RG to asphalt or bitumen, there are some physical properties that you're supposed to actually get introduced to. One, as you move from refinery gas to petrol to naphtha to kerosene to diesel to lubricating oil to fuel oil and bitumen, you should note this. One, the intensity of color increases. So those components just below or just down the fractionating column are darker in appearance. The ones just at the top of this column are less darker. But as you move downwards, they tend to become darker. The intensity of the color increases as you move from one fraction to another. You can't compare the intensity of how dark kerosene looks like to how bitumen looks like in terms of their appearance. They're different. Number two, as you move from refinery gas to bitumen, flammability decreases. That means the ability for these fractions to catch fire decreases. So that means RG or LPG is more flammable than bitumen or asphalt. So it means when a matchstick is lit, it is easier for RG to catch fire than bitumen. So flammability decreases. Flammability decreases. The ability to catch fire decreases down the fractionating column. Something else to add on these physical properties is this. You should also note that as you move downwards from LPG or RG to bitumen, stroke residue, stroke asphalt, there's always the ability of these fractions being able to have their boiling points increasing. Why? Because you can try to imagine most of the components of LPG have up to 4 carbon atoms. And you're told that bitumen can have up to 70 carbon atoms. Just look at that. So trying to imagine, this has 4 carbon atoms and this has 70 carbon atoms. So each one has more intermolecular forces of attraction. It is bitumen. So the more the number of carbon atoms moving downwards, the more the intermolecular forces of attraction. And the more the intermolecular forces of attraction, the higher the boiling point. Why? Because the more the intermolecular forces of attraction, the higher the temperature required to break this increased number of intermolecular forces of attraction. So you cannot be able to compare the boiling point of a substance having 4 carbon atoms in its structure and another substance having 70 carbon atoms. The one with the 70 carbon atoms has more intermolecular forces of attraction and covalent bonds between the carbon atoms. So with the 70 carbon atoms, there are more intermolecular forces of attraction and more covalent bonds between the carbon atoms, forming the structure or the compound. So the more the types of bonds or fractions having more intermolecular forces of attraction, the higher the boiling point of that fractional component. So moving downwards, the boiling point and the melting point of these fractions can increase depending on the state in which they can be able to get found. Now, there's something called viscosity, the easiness of a liquid to flow. How easily a liquid can flow. You see, if you compare water and porridge or water and honey, you can realize that honey and water have different viscosities. Honey is more viscous, so it easily does not flow. Water is less viscous, it easily flows. I think you can be able to get the difference. Viscosity is the easiness of a liquid to flow. So when you compare water and honey, water is less viscous, honey is more viscous. To mean water easily flows and honey does not easily flow. And of course, viscosity must be related to a particular force, now in terms of physics, that can actually be able to offer resistance to the flow of a fluid or a liquid. So there's more in terms of viscosity in honey and less in terms of viscosity in water. So as you move down the fractionating column, these components become more viscous. Their ability to easily flow decreases. The force that can offer resistance to their flow increases. So they do not easily flow as you move downwards the fractionating column. So to mean asphalt, bitumen or residue is more viscous, does not easily flow. But LPG or RG is less viscous, easily flows. That's the difference between those two. So petrol and diesel do not have the same viscosity. To mean petrol can easily be able to flow, but diesel does not easily flow. So they have different viscosities. They have different viscosities. So those are just some of the physical properties that you're supposed to actually get introduced to. And of course, to add on this, you can actually be able to realize that their solubility in water decreases down the fractionating column. To mean LPG is more soluble in water than bitumen. I repeat, LPG is more soluble in water than bitumen. And of course, generally, their solubility in water is very less. Why? Because water is a polar substance while these components are non-polar. And of course, we said, for example, water and ethanol are miscible. So you can be able to actually explain that in terms of their polarity. So it means these components or fractions of crude oil cannot easily dissolve in water because they are non-polar and yet water is polar. And of course, a polar substance is a substance that is actually partially positive and partially negative. Look at that. Because when you look at the structure of water, you realize that water has a partially positive hydrogen part and a partially negative oxygen part. To mean that the shared pair of electrons between a hydrogen atom and an oxygen atom has to actually constitute this. One, the electrons are strongly attracted to the oxygen atom, which is more negative, and they are less attracted by the hydrogen atom, which is actually less negative and more positive. So the ability of an oxygen atom in a water molecule to strongly attract the shared pair of electrons onto it makes it to become electronegative. And the ability of a hydrogen atom to become less able to attract the shared pair of electrons onto itself makes it to become electropositive. So that means water molecules end up possessing a partially positive part, which is a hydrogen part, and a partially negative part, which is an oxygen atom. At the end of the day, it becomes a polar substance. So, and we also need to explain more in terms of the density. As you move downward, you've actually said the carbon atoms increase. Of course, the density increases down the group. Why? Density and mass are directly proportional to each other. So the greater the mass of a particular component of crude oil, the greater the density of that component of crude oil. So that tells you that LPG is less denser than bitumen. So bitumen is denser than LPG because it has a greater mass because of the increased number of carbon atoms. So the greater the mass, the greater the density of that substance. So density increases down the fractionating column so that The least dense is LPG and the most dense is bitumen. And if you look at the molecular mass, of course, the more the number of carbon atoms in terms of organic chemistry, the greater the molecular mass. So bitumen has the greatest molecular mass with 70 carbon atoms, while LPG has the least molecular mass with a maximum of 4 carbon atoms. So the molecular mass increases down the group as the number of carbon atoms increases. Now, if we have to actually take ourselves back to this aspect of trying to see how these components are very useful to our environment, we shall be able to actually mention this. LPG or refinery gas has at least 4 very important alkanes for us to mention. 1, methane, ethane, propane, and butane. And in most cases, LPG or RG or refinery gas qualifies to be used in gas cylinders for domestic purposes during the cooking process. So LPG or refinery gas, it is normally placed in gas cylinders and transported for domestic purposes in terms of cooking. A very important component of LPG or RG, which is butane, gets used in laboratories in different research centers and schools as a laboratory gas. So the gas cylinders you always find in our schools is filled with butane as a component of refinery gas or liquefied petroleum gas. Moving downwards to petrol. Petrol is actually used, for example, in petrol engines and a fuel. We've actually had a chance of getting vehicles being able to get powered by petrol. So different petrol engines can only be able to use petrol as a fuel and not diesel. So petrol engines can maximize on the use of petrol as a fuel to get powered. And petrol in most cases can actually be able to get used in making a more refined, fuel called gasohol. It gets mixed with what? Alcohol. So petrol can also get called gasoline. And this petrol or this gasoline can get mixed with ethanol or alcohol. And they can be able to form a fuel called gasohol. Gasohol can be able to get used as a more refined and more engine-friendly fuel in different engines in our environment. So petrol or gasoline can get mixed with ethanol to form a fuel called gasohol that becomes more engine friendly. That becomes more engine friendly, preventing any form of anti-knock in the engines. Naphtha is used to actually get used as a chemical. It's something normal in industry. So if someone wants to maximize on the manufacturing of naphthalene, then they can actually be able to use naphtha as a chemical. And of course, naphtha can also get used as an industrial chemical for different purposes, as a raw material to manufacture different substances, including dyes and drugs. Paraffin or kerosene is used for domestic purposes during lighting or cooking. Kerosene lamps can use kerosene for lighting. Different stoves or kerosene stoves can use kerosene for the purpose of cooking. The same kerosene or paraffin can get more modified and other substances like the antifreezers getting added to it to get used as a jet fuel. Look at that. So the kerosene or the paraffin can get mixed with other chemicals or substances like antifreezers and then get used as a fuel in jets. And you can have diesel getting used as a fuel in diesel engines. You see? And you can have lubricating oil getting used as a lubricant, you see, in different engine parts. Where there's movement in engine parts, to reduce friction, you always apply the lubricating oil. You see, we have actually been using kerosene in jet fuels and as well lubricating oil in engine parts to reduce friction and prevent rusting. Look at that. So in any moving engine parts, in any engine part that is actually movement, we always add lubricating oil to serve as a lubricant to reduce friction and be able to absorb any excess heat getting absorbed in the engine parts, and as well prevent the parts of the engine from getting corroded by air and water, because you cannot apply some other means of preventing rusting in the engine parts like galvanizing, enameling, sacrificial protection, and other methods. So you can be able to use it for the lubricating oil. And of course, fuel oil is used in factories and large ships as a fuel. So in factories, manufacturing different substances, and large ships moving within the body parts of water bodies, you see, you can be able to have this getting used as a fuel. So in any water bodies, maybe what you call the large ships, and in any factories, when you can be able to actually have different substances getting manufactured, we can utilize this fuel oil as a very important fuel. And lastly, bitumen, residue, or asphalt can get used in road tarmacking or road construction. Road tarmacking or road construction. So let's just get to the questions. Give the possible roles of fractions 4 and 6. I've actually answered that. You actually had on the state. Explain the following, giving relevant examples from the above diagram. Viscosity, I've actually told you about viscosity. Color, I've told you about color. Give one way of increasing the efficiency of the process. You can make the fractionated column to be a bit more longer. The fractionated column can be made more longer so that those fractions can distill off at very specific fractions, preventing a fraction being impure because of it having more than one component. And maybe you can be able to use the shelves so that they can be able to actually allow these fractions to distill off at different temperatures. Shelves, or making the column very longer. And of course, increasing the efficiency of the heating process. Why are the fractions impure? Because to some extent, the separation cannot be very 100% pure or efficient. So at the end of the day, one fraction may contain more than one component, making that fraction to be impure. Differentiate between thermocracking and catalytic cracking. Thermocracking is the breaking down, the decomposition of a particular substance or hydrocarbon, for example, an alkane, into smaller fractions, such that at the end of the day, temperature is used. For example, at the end of the day, you realize that propane, which is C3H8, can undergo what you call thermocracking at a temperature of 100 or 400 degrees Celsius to 700 degrees Celsius, such that you can be able to have methane getting formed, okay, ethene and propane and hydrogen gas. I'll just put here 2. So 1, 2, 3, 4, 5, and 6. So you can have this propane as a longer chain hydrocarbon getting to that point of getting broken down or decomposed by the use of heat, and that gets called thermocracking. The range of the temperature to be used can be 400 to 700, and that can make it to decompose to shorter chain alkane and alkenes. So ethane, propane can get decomposed as a longer chain alkane to form a shorter chain alkane, which is actually methane, and shorter chain alkenes, that is ethene and propane, and hydrogen gas actually produced. So this can be a very good source of hydrogen gas to get used in the Haber process during the manufacturing of ammonia gas, or get used in the hydrogenation process where margarine is formed when oils are hardened. You see, so there's something called hydrogenation. Hydrogenation is where hydrogen gets bubbled through oils. So the oils get hardened to form margarine. And that requires hydrogen gas, of course. That is why it's called hydrogenation, and as well nickel catalyst to speed up the process. And someone talks about catalytic cracking. Most scientists use what you call zeolite. Zeolite is a mixture of alumina and silica, aluminium 3 oxide and silicon 4 oxide or quartz. So when someone cracks a longer chain alkane using temperatures, they may require a temperature of around 400 to 700 degrees Celsius. And if someone talks about using a catalyst or catalytic cracking, they may require a catalyst called zeolite, which is a mixture of two catalysts, alumina and silica, aluminium 3 oxide and silicon 4 oxide, that can still be able to actually crack that longer chain alkane to give us shorter chain alkane and alkenes and hydrogen gas that is also produced. So at a stage where someone uses a catalyst, you may not require very high temperatures, require actually a lower temperature to still facilitate the process of doing what we call the cracking process. Thank you so much for your listening, and let's meet in our next lesson.